Pluto was the first Kuiper Belt object discovered, and for about 60 years, it was the only known member of this region. It wasn't until November 2, 2015, that the world saw its first image of a Kuiper Belt object, a remarkable photograph from space that was considered groundbreaking. However, recent advancements have shifted this perspective significantly. The James Webb Space Telescope has now provided the sharpest image of the Kuiper Belt ever captured, revealing features unlike anything previously imagined. The Kuiper Belt is situated in the outer solar system and forms a frigid, donut-shaped zone extending beyond Neptune's orbit, the eighth planet from the Sun. Initially, the shape of the Kuiper Belt was its most intriguing feature, but it has since become clear that this region holds some of the most fascinating aspects of our solar system. Named after the astronomer Gerard Kuiper, whose mid-20th century research laid the groundwork for understanding this region beyond Pluto, the Kuiper Belt was not directly discovered by him. In 1951, Kuiper published a scientific study suggesting the presence of objects beyond Pluto. His research focused on the likelihood of these objects but did not predict their specific features or organization. Pluto was once considered the defining component of the Kuiper Belt. However, it is now understood that Neptune's orbit, rather than Pluto's, defines the belt's inner boundary. The gravitational influence of Neptune has significantly shaped the dynamics of the Kuiper Belt. Although Kuiper's predictions were not perfectly aligned with later discoveries, his pioneering work remains highly regarded among astronomers. The concept of the Kuiper Belt and its association with objects beyond Pluto has become closely linked with Gerard Kuiper. In 1930, astronomer Clyde Tombaugh discovered Pluto in what is now known as the Kuiper Belt. At the time of Pluto's discovery, the understanding of the outer solar system was limited, and astronomers did not anticipate a substantial population of icy worlds beyond Neptune. The traditional model of the solar system included the inner rocky planets, the gas giants, and the outermost frozen giant Neptune. Pluto's discovery, with its eccentric and inclined orbit, initially led scientists to consider it a solitary planet. It wasn't until 1992, 62 years later, that a second Kuiper Belt object was discovered, revealing that Pluto was part of a larger population of objects in the outer solar system. The discovery of additional Kuiper Belt objects, KBOs, confirmed the existence of this region, which hosts a diverse array of cold worlds beyond Neptune. Pluto's significance in astronomical history lies in its initial classification as the ninth planet, a status it held for several decades. However, as understanding of the Kuiper Belt expanded and larger KBOs were discovered, the International Astronomical Union redefined planetary criteria in 2006, reclassifying Pluto as a dwarf planet. Despite this change, Pluto remains a crucial discovery, having opened the door to exploration of the Kuiper Belt. This region is considered an extension of our solar system, sharing the same cosmic neighborhood and influenced by the Sun's gravitational forces. While the 8 major planets, including Neptune, dominate the inner solar system, the Kuiper Belt extends the solar system's borders into the outer regions. Characterized by a collection of icy objects including dwarf planets, asteroids, and comets, the Kuiper Belt is believed to be composed of remnants from the early solar system, dating back approximately 4.6 billion years. This material is expected to have preserved conditions and materials from that time. The Kuiper Belt is home to Pluto and its moons, as well as additional dwarf planets like Haumea, Makemake, and Eris. It also contains a diverse variety of tiny icy bodies, which are not found elsewhere in the solar system. The Kuiper Belt is significantly larger than the main asteroid belt, which consists of rocky objects mainly between Mars and Jupiter. The Kuiper Belt is more extensive and remote, estimated to be 20 to 100 times more massive than the asteroid belt, containing a larger number of objects and greater overall mass. This substantial mass contributes to the surprising length of time it took to discover these objects. Despite the delay in discovery, the Kuiper Belt is crucial to the solar system, hosting a wide range of celestial entities, including dwarf planets like Pluto, Haumea, Makemake, and Eris. Pluto, discovered by Clyde Tombaugh in 1930, was originally classified as the ninth planet. However, the International Astronomical Union revised the criteria for planetary status in 2006, reclassifying Pluto as a dwarf planet. With a diameter of approximately 2,377 kilometers, Pluto orbits with other significant dwarf planets in the Kuiper Belt. Research into Pluto has greatly enhanced our understanding of this distant region. Haumea, discovered in 2004 by Mike Brown's team, adds to the diversity of the Kuiper Belt with its distinctive elongated shape, likely due to rapid rotation. Haumea, with a diameter of about 1,960 kilometers, has provided valuable insights into Kuiper Belt objects. Makemake, another discovery by Mike Brown's team in 2005, exhibits unique features with a diameter of roughly 1,430 kilometers. Despite lacking a large atmosphere, its bright surface, composed of methane, ethane, and tholins, makes it one of the brightest objects in the Kuiper Belt. Eris, discovered in 2005 as well, is somewhat smaller than Pluto but more massive, with a diameter of approximately 2,326 kilometers. Eris's discovery contributed to the re-evaluation of planetary concepts and broadened our understanding of the variety and dynamics of Kuiper Belt objects. Together, these dwarf planets offer critical insights into the composition and evolution of the Kuiper Belt and its role in the solar system's history. Many people confuse the Kuiper Belt with the Oort cloud, but they are distinct. The Kuiper Belt is more densely populated with objects and is believed to be a source of short-period comets, which have shorter orbital periods. In contrast, the Oort cloud is a more distant, spherical region surrounding the entire solar system, potentially extending from about 2,000 to 20,000 astronomical units from the Sun. The Oort cloud is made up of frozen bodies, often compared to dirty snowballs, and is the suspected source of long-period comets with highly elliptical orbits. Despite their differences in location and shape, both the Kuiper Belt and the Oort cloud are repositories of frozen bodies and potential sources of comets. These comets, composed of ice, dust, and volatile chemicals, become visible as they approach the Sun, developing bright comas and tails due to solar wind. The amount of material in the Kuiper Belt today might be just a fraction of its original mass. Current material is essentially remnants, with much of the original material having long since evaporated. The NICE model, a theoretical framework, suggests that significant orbital adjustments occurred in the outer solar system, involving Jupiter, Saturn, Uranus, and Neptune. This model proposes that these large planets did not always occupy their current orbits but underwent rapid changes. The interactions between these planets likely caused dramatic alterations in their orbits, leading to the scattering, expulsion, or redistribution of Kuiper Belt material. Consequently, the Kuiper Belt is currently in a state of steady degradation. Collisions between objects in the belt can fragment them into smaller Kuiper Belt objects, some of which may become comets while others are destroyed. Dust from these collisions can be expelled from the solar system by solar wind. The overall mass of the Kuiper Belt material is estimated to be no more than about 10% of Earth's mass. While this may seem small, it still represents a significant number of Kuiper Belt objects. Many of these objects have moons, and some exist as binary systems, where two objects of similar size or mass orbit a common center of mass. These binary pairs can have various orbital properties, with some forming contact binaries, where the two components are in physical contact and exhibit a characteristic peanut shape due to their combined gravitational forces. NASA's exploration of the Kuiper Belt began with Pioneer 10, launched on March 2, 1972. Pioneer 10 was a revolutionary spacecraft designed to explore Jupiter and its atmosphere. It made history as the first spacecraft to pass through the asteroid belt and, in 1983, became the first to traverse the Kuiper Belt region. Although it did not explore any cold worlds, as none were identified aside from Pluto at the time, its mission contributed crucial data about the outer limits of the solar system. Later missions, such as Voyager 2 and Cassini, furthered our understanding of the outer solar system. Voyager 2's visit to Neptune's moon Triton in 1989 and Cassini's research of Saturn's moon Phoebe in 2000 provided valuable information on these celestial bodies. Some of these moons are believed to have originated from the Kuiper Belt and were captured by their respective planets' gravitational forces. The New Horizons spacecraft made history with its first-ever flyby of Pluto in 2015. During its mission, New Horizons captured images of a Kuiper Belt object known as 1994 JR1, an asteroid about 90 meters in diameter, providing significant data on Kuiper Belt objects. In 2014, the Hubble Space Telescope played a crucial role by identifying 3 potential Kuiper Belt objects for NASA's New Horizons mission and spotting 2 frozen mini-worlds near the solar system's boundary. These discoveries led to an extended search for suitable objects for New Horizons to investigate after Pluto. Hubble's contributions to Kuiper Belt research date back to 2003, when it obtained images of a Kuiper Belt object designated 2F53. This object, initially detected in March 2000, was significant in guiding Hubble's observations. The 3 newly discovered Kuiper Belt members revealed by Hubble were unusually faint, requiring computer analysis to locate them. The advanced camera for surveys on Hubble confirmed that these objects were gigantic. The James Webb Space Telescope has since provided unprecedented capabilities for observing and analyzing the Kuiper Belt. Utilizing infrared technology, the telescope can detect objects with temperatures above absolute zero, making it easier to gather information about the cold, distant Kuiper Belt. The Kuiper Belt is a region of the solar system that has long intrigued astronomers due to its potential insights into the early solar system. Beyond the orbit of Neptune, this vast and frigid expanse is teeming with ancient remnants from the solar system's formative years. As we delve deeper into understanding the Kuiper Belt, we also gain perspective on its role in shaping our current view of planetary science. In addition to the well-known dwarf planets such as Pluto, Haumea, Makemake, and Eris, the Kuiper Belt is home to numerous smaller objects, many of which remain unexplored. These include icy bodies, comets, and other trans-Neptunian objects, TNOs. The sheer number and diversity of these objects suggests that the Kuiper Belt is a dynamic and evolving region, where new discoveries are continually being made. A key component of Kuiper Belt research involves studying the orbital dynamics of its objects. The orbits of Kuiper Belt objects vary widely, from nearly circular to highly elliptical. This variation in orbital characteristics provides valuable information about the history and evolution of the solar system. For example, the presence of objects with highly elliptical orbits might suggest past gravitational perturbations or interactions with other celestial bodies. In recent years, advancements in observational technology have significantly enhanced our ability to study the Kuiper Belt. Instruments such as the Spitzer Space Telescope and the Atacama Large Millimeter/Submillimeter Array, ALMA, have provided additional insights into the composition and distribution of Kuiper Belt objects. Spitzer's infrared observations have helped identify and analyze the thermal emissions from these distant objects, offering clues about their surface compositions and temperatures. ALMA, with its array of high-precision radio telescopes, has contributed to our understanding of the Kuiper Belt by observing the faint emissions from dust particles and icy grains within the belt. These observations have revealed the presence of small, icy bodies that are crucial for understanding the belt's overall mass and structure. The study of the Kuiper Belt also intersects with the field of planetary defense. The Kuiper Belt is a source of near-Earth objects, NEOs, and comets that can potentially impact Earth. Understanding the distribution and trajectories of these objects is crucial for assessing potential risks and developing strategies for impact mitigation. For instance, the observation of certain Kuiper Belt objects with orbits that intersect Earth's path has led to the identification of potential impact hazards, prompting further investigation and monitoring. Moreover, the Kuiper Belt plays a role in understanding the formation and evolution of planetary rings. Observations of ring systems around other planets, such as Saturn, have provided analogs for studying the potential formation of ring systems around dwarf planets and Kuiper Belt objects. The processes that lead to the formation of planetary rings, including collisions and tidal interactions, are also relevant to understanding the dynamics of the Kuiper Belt. As we look to the future, upcoming missions are expected to continue expanding our knowledge of the Kuiper Belt. NASA's upcoming missions, such as the Lucy spacecraft, will study ancient asteroids and comets that may have originated in the Kuiper Belt. Lucy's journey to the Trojan asteroids of Jupiter will provide further insights into the early solar system and the role of the Kuiper Belt in shaping planetary formation. Additionally, the European Space Agency's ESA Hera mission aims to explore the binary asteroid system Didymos, which includes a small moonlet orbiting a larger asteroid. While not directly targeting the Kuiper Belt, Hera's mission will contribute to our understanding of similar binary systems, which can offer analogs for studying Kuiper Belt binary objects and their interactions. The Kuiper Belt also has implications for understanding the potential habitability of distant exoplanets. Research into the composition and distribution of Kuiper Belt objects provides insights into the conditions necessary for planet formation and the potential for habitable environments in other star systems. By studying the materials and processes in the Kuiper Belt, scientists can refine models of planetary system formation and assess the likelihood of discovering habitable planets around other stars. Furthermore, the Kuiper Belt study has cultural and philosophical implications. As we explore this distant frontier, we are continually reminded of the vastness of the cosmos and our place within it. The discoveries made in the Kuiper Belt challenge our understanding of the solar system and push the boundaries of human knowledge. They inspire curiosity and wonder, reflecting our innate desire to explore and understand the universe. In summary, the Kuiper Belt represents a critical component of the solar system's outer regions, offering valuable insights into its formation, evolution, and dynamics. The continuous advancements in observational technology and the upcoming missions are set to enhance our understanding of this distant and enigmatic region. The study of the Kuiper Belt not only expands our knowledge of planetary science, but also has implications for planetary defense, ring system formation, and the search for habitability beyond our solar system. As we continue to explore this icy frontier, the Kuiper Belt remains a testament to human curiosity and the relentless pursuit of knowledge.